I believe that water will one day be employed as a fuel, that hydrogen and oxygen, which constitute it, used singly or together, will furnish an inexhaustible source of heat and light, of an intensity of which coal is not capable. I believe then that when the deposits of coal are exhausted, we shall heat and warm ourselves with water. Water will be the coal of the future. Energy is the central commodity of global civilization. Without huge energy resources to supply the growing needs of humanity, economic and social progress would stagnate, and the world would plunge into a new dark age. Today, we expend the equivalent of 2,000 barrels of oil per second, and this is growing, especially in developing nations. In the late 20th century, wars have been fought over the control of oil buried beneath shifting desert sands, and this source of energy will one day run out, though perhaps long after irreversible environmental damage has been done. New clean energy sources are sorely needed to replace polluting fossil fuels. Many say that all the peoples of the world, especially in the industrialized nations, need to scale back their energy consumption, ending their hopes for a brighter future. Others say our salvation lies in renewables, such as solar and wind power. However, the limitations of these passive energy systems, with their dependence on favorable weather conditions and locations, preclude them from being the ultimate energy solution. Yet what if there were an ultimate solution of virtually infinite clean energy from a substance almost no one had previously suspected? The very water that covers 70% of the surface of our planet and gives life to all biological systems. In 1989, the prospect of a water fuel age foretold by Jules Verne over a century ago came into sharp focus with the announcement of a startling discovery at the University of Utah. Two respected chemists, Dr. Martin Fleischmann and Dr. Stanley Pons, announced that they had achieved the unthinkable, an inexhaustible source of energy that they could demonstrate with a simple electrochemical cell.
Basically, we've established a sustained nuclear fusion reaction by means which are considerably simpler than conventional techniques.
They claimed that they had discovered a heretofore unknown nuclear-like reaction that would make water a powerful fuel for the future. It became known as cold fusion because it apparently delivered fusion energy like that produced in the sun or by hydrogen bombs. Yet not at millions of degrees, but much closer to room temperatures. Moreover, it emitted no deadly radiation. Ironically, the press conference came less than 12 hours before the Exxon Valdez ran aground off the coast of Alaska, spilling millions of gallons of oil into pristine waters. It is now a decade later, with a world so desperate for new sources of clean energy. What happened to the promise of cold fusion? It was a big story then, making headlines around the world. But all of a sudden, it died out, and we were told that it was just another false promise. Was cold fusion too good to be true? A mistake by overzealous scientists? Or is it a real phenomenon, just not easily understood? And if so, why haven't we heard much about it since then? Is it just wishful thinking, or are we about to witness the coming of a new energy revolution as we uncover the secrets of making fire from water? Hollywood movies often exaggerate reality in order to tell a compelling story that will entertain and enthrall. Yet Hollywood's best writers could hardly dream up a more dramatic tale than the true story which began with Fleischmann and Pons and is still unfolding as one of the most intense controversies in the history of science. Fusion is a process that releases huge amounts of energy when two atomic nuclei, usually hydrogen isotopes, collide and fuse together. Theoretically, this can occur only at extreme temperatures. For decades, scientists at Princeton, MIT, and other institutions have been pouring billions of government dollars into building plasma fusion reactors, magnetically ringed vessels called tokamaks, that could contain this hot fusion reaction. Their goal? To bring the nuclear fire of the sun down to Earth using the hydrogen in water as fuel. Although much has been learned in the quest for controlled fusion, success has been elusive, and the promise of hot fusion remains as distant as ever. To date, not one extra watt of power beyond the electrical power fed in has ever been generated. Water itself is quite a mysterious and powerful substance. Given enough time, it can erode steel and rock. It is composed of hydrogen and oxygen, two of the most reactive elements on Earth. Science has also known for over 200 years how to extract hydrogen and oxygen gas from water through the process of electrolysis. It was from this field of electrochemistry and not nuclear physics that there emerged a revolutionary idea of a new kind of fire from water. In the 1980s, Fleischmann and Pons used their own money to conduct experiments for 5 years. They passed a current through an electrochemical cell containing heavy water, or deuterium oxide. One of the electrodes, the negatively charged cathode, was made of the precious metal palladium. The electrical current separated individual deuterium nuclei, or deuterons, from the heavy water and forced them to pack tightly into the palladium cathode. What happened next inside the palladium at the atomic level remains a mystery and became the subject of intense debate. Whether it was actual nuclear fusion or some other as yet unknown phenomenon, the result produced far more excess heat energy than any known chemical reaction. Why is such a phenomenon so astonishing? Why did it provoke such outrage in the physics community? To most classically trained physicists, the concept of low-level nuclear reactions producing significant heat energy was inconceivable. The nuclei of atoms are all positively charged and naturally repel one another. They don't want to come together, to fuse, except at millions of degrees. And when they do, deadly radiation is released. When Fleischmann and Pons claimed that they had created nuclear reactions at room temperature, university and government laboratories around the world immediately set out to replicate the experiment, which, superficially, looked simple. Some reported similar anomalous heat and nuclear byproducts such as tritium, low-level neutrons, and helium. Others at major universities such as MIT and Caltech claimed they had found nothing.
The idea that two chemists could be doing this on a tabletop really sounded very almost Alice in Wonderlandish, I must say. So I think our reaction was not unlike that of other physicists who thought, on the one hand, gee, that'd be marvelous if they're doing it, and then on the other hand, my God, chemists doing it for probably pennies compared to what physicists have taken from the public coffer over the last 40 years, in the order of $40 billion to do hot fusion. So the nuclear physics community said, well, you know, the nuclear physics of this is looking very strange. It doesn't seem to be right. Where are the neutrons? Where are the gamma rays? And eventually, I think because of this bad nuclear physics, and because of the fact that people were having difficulty reproducing this, the physicists threw out the good baby, which was the excess heat effect, along with the bad nuclear interpretation bathwater. That was very unfortunate.
At SRI International in Menlo Park, California, Dr. Michael McCubry was one of the first scientists to replicate the cold fusion effect.
Fortuitous or not, in the first experiment that we ran some 3 or 4 months after the initial announcement, we saw some evidence of excess heat, which has really sustained me ever since. Having seen the effect with my own eyes, the claims from a few that this is impossible, inconsistent with all known laws of nuclear physics, these suggestions are in fact irrelevant. There is no theoretical objection to cold fusion. It's just unlikely given our experience with hot fusion.
At Texas A&M, a group led by Professor John Bockris, who is widely regarded as one of the world's greatest electrochemists, reported finding the hydrogen isotope tritium, a key signature that some unusual nuclear reaction was going on.
The first thing was this thing called tritium, which was a sub-form of hydrogen which should not exist except in extremely tiny quantities. We found that by working these cells of Fleischmann and Pons containing lithium hydroxide and deuterium oxide, that we could produce this tritium in great abundance, let's say at 10,000 times more than it ought to be there, as it were. And let me stress that we couldn't do it every time, but about one result in 5 or one result in 4, and eventually we worked up to 2 results out of 3, we could produce tritium. That was the first thing, and in a way it was the first clear proof of the phenomenon.
Halfway around the world, at the Bhabha Atomic Research Center in India, Dr. Mahadeva Srinivasan provided confirmation.
Within a few weeks, within 2 or 3 weeks, we got the first results, and several groups started saying, yes, we are seeing excess heat, and but the most important and unbelievable phenomenon at that time was the observation of tritium.
Back at Texas A&M, Bockris's group found themselves under attack. Science magazine writer Gary Taubes wrote a stinging article that insinuated that someone in the group had spiked the samples with tritium. Although unfounded and eventually proved untrue, the allegation effectively dampened Bockris's remarkable claims.
Well, I was 69 years old at that time. I took the attitude, suppose they fire me, right? It doesn't really matter. I'd had my career. The worst they could do would be to say, go, your tenure is withdrawn. And therefore I wasn't frightened. And I went on saying the truth and publishing what we'd got. But finally the university revolted against this. And they set up an inquiry, they called it rather sinisterly. The accusation was that I had carried out misconduct of research, you see, that I shouldn't have worked on these things. And they decided that the accusations were totally groundless, and they published all this. But then they started all again about 6 months later, and they had another committee. It was this time, when my lawyers asked the university what the second inquiry was about, they were told, it's an ad hoc committee. What's that? we have nothing further to tell you. And so this went on for 11 months of constant meetings and inquiries and so on. And I'm quite sure that they were trying to find an excuse to end my tenure, you see.
Getting tenure in most traditional science departments depends on doing mainstream research. Being a leader in mainstream research, but doing mainstream research, and not doing fringe area research, investigating things like cold fusion. Once you're tenured, it's a bit of a different story in that in principle you can investigate any field you like, and people have done that. But even then, the way things are connected with money, power in universities today, your life can be made rather difficult if you are identified with those areas.
Finally, they came out okay. I mean, they gave me another letter. I'd had the letter of complete exoneration. This time it said that they had spent this 11 months and had found that I had never done anything, the phrase used were, that contravened the rules of procedure of this university, or something rather formal and stuffy like that.
Normally we'd say someone's innocent until proven guilty, and you'd be given the opportunity to have a trial rather than having an article written about what you've done wrong and identify as being guilty in the press rather than due process. Anyway, all these things were happening, and it just makes one sad.
But I think the main part was that I had done work which was against the paradigm, and that was what they were really upset about. You know, people said that they'd been to other universities and people had laughed at it and said, "What the heck are you doing, trying to disprove the laws of nuclear physics?" And of course that's exactly what we were doing, and succeeding, you see.
Cold fusion scientists long ago put the issue of measurement accuracy to rest. Like good scientists, they tried to prove themselves wrong. Still, the excess heat findings persist. Since 1848, it has been known that a certain amount of heat is required to change the temperature of a given amount of water. At premier labs such as SRI International, Dr. Michael McCoubrey has determined that the effect is neither fleeting nor difficult to measure. The cold fusion cell is enclosed in a calorimeter, which has thermocouples at various key points to read the temperatures. The experiment looks extremely complex on the surface, but fundamentally it is simple. An ordinary coffee maker provides an analogy. Cold water goes in, hot water comes out. The temperature of the water is read before the electrical input is supplied, and then again as it rises. Some of the heat is lost during the process, but the result is obvious. McCoubrey's calorimeter works in a similar way, but with an accuracy of 1/1000th of a degree. The cooling water flows in a steady stream and passes the inlet thermocouple, which measures the temperature. It swirls around the cell, cooling it down and carrying off the heat. When it exits, the outlet thermocouple measures the temperature again. Inlet temperature is subtracted from outlet temperature to determine how hot the water has become during its passage. Meanwhile, input electricity to the cell is monitored. During an experiment with a palladium cathode for the first week, while the cathode is loading, no excess is detected. Later, in a successful test, the outlet water temperature climbs, and total output energy from the cell exceeds input. This is called excess energy. Excess heat is measured at least 30 times higher than the background noise, often much higher. Professor George Miley, director of the Fusion Studies Laboratory at the University of Illinois, was one of the few editors of a peer-reviewed physics journal to accept papers on cold fusion.
Positive measurements of helium, continued reports of heat burst, the tritium measurements that people have done. While they're not reproducible always, the fact that they occur kept encouraging me. Let's take tritium as an example, which is work that Tom Claytor has done at Los Alamos. At a meeting about a year ago where he was presenting his material, I asked him what I thought was a key question. Have you convinced your management at Los Alamos that tritium is real? Because it seems like such a convincing case. And he said, no, I haven't. I said, why not? He said, well, the problem is that I only get a positive results 3 times out of 10. Now think about that. If it happens once, the inquisitive scientist should say, well, how did it happen? Let's find out how we can make it happen again and how we can ultimately make it happen consistently.
The tritium work was the first indication to me that there was a reality, and then Claytor at Los Alamos also got positive results, and so did Howard Menlove. And they're people that I respect and could talk to personally. I then wrote a review of the field, looking at everybody's work worldwide, and talked to many of the people that were involved in the work. And on the basis of that review and personal knowledge of my own work and other people's, it became fairly clear that there was a very strange phenomena occurring here.
There is clearly evidence of anomalous excess heat which occur in these experiments under some rather difficult to achieve conditions, but rather well-defined conditions. There are also, in similar experiments sometimes, and rather dissimilar experiments sometimes, evidence of an anomalous nuclear process. And both anomalies are worth pursuing. It's my suspicion, my bias, if you like, that the 2 anomalies are in fact connected, that there's an underlying fundamental mechanism which connects the 2. I would be satisfied with an accurate description of the method by which the lattice, the palladium crystalline system with deuterium inside it, how that crystalline system interacts with the nuclear process.
There is something new coming up. And so, like everybody, you know, professors who teach physics hate to change their courses. And generally, they don't appreciate monsters which crop up and which cannot be explained within the frame of the present knowledge.
Since prehistoric times, people knew that a certain amount of fuel always gave a certain amount of energy. Whether burning wood, coal, or oil, the process is a simple chemical reaction. Then in 1896, Henri Becquerel discovered radioactivity. He found materials that do stay hot for weeks. Later, Madame Curie and others discovered that some materials, such as radium, produce heat for centuries and even millennia. 1,000,000 times more energy can be produced by radium than by a chemical fuel weighing the same. It's been known since then that radioactivity not only produces heat, but never consumes the fuel. No change would be observed until thousands of years later, when the radium turned to lead, with only a minute amount of mass lost in the transfer to heat energy. Radioactive plutonium glows for decades, powering unmanned probes that venture out through interstellar space. If a cold fusion cathode were a typical chemical reaction, it would get hot and within a few minutes it would be consumed. The reaction would stop. In fact, there are no known chemical fuels in the cell. It contains mostly water, which is chemically inert. Water cannot burn. Yet in experiments, cold fusion heat has continued for days, sometimes weeks. The only thing modern science knows that is consistent with this is a nuclear reaction. However, it is conceivable that there may be a process even more powerful than nuclear reaction that physics does not yet understand. That is the mystery of cold fusion. For though scientists have identified telltale nuclear changes in cold fusion materials, they cannot agree on what exactly is this reaction or set of reactions that produce excess heat.
There are various, at least 3 conflicting interpretations. One of them is just it's some property of hydrogen or deuterium inside matter, or it's a property of the particles themselves, which is revealed by the absorption within solid matter.
Well, our critics would say that the problem with cold fusion is that there is no theory to describe it. The problem is completely different. The problem is that there are far too many theories which purport to describe the same set of observations, and no more than one of these theories can be correct. So we are embarrassed with an excess of theories, which means that it's difficult for me, an experimentalist, to decide amongst the theories to see which one I should examine and test.
Inside the metal lattice exists a world so spacious and expansive that hydrogen atoms can nest in a virtually 1-to-1 ratio with each atom of palladium. This creates a metastable state, which can sometimes release enormous energy. But how that happens is what theorists like the late Nobel laureate Julian Schwinger, MIT's Peter Hagelstein, and other brilliant minds have attempted to explain, and therefore reliably predict.
It might have 10 to the 10th dimensions.
Still, the lack of a theoretical framework does not deter those who see the potential for commercial devices.
At the moment, 10 watts per cc is about the maximum we can get regularly. There are odd people here and there who claim much more, and I believe them, but you know, how often can they get it? That's the point. Now, were we able to get 100 watts per cc, well, then we would have a fantastic, and reproduce it. Then we would have a source which would be better than any nuclear energy we've had so far, and also, of course, completely clean, because it produces helium, which is totally harmless.
This experiment very much follows along the thought process of Les Case. And behind me you see 5 different sets of apparatus. The big vessel here is one of Les Case's, he calls them footballs. It's a stainless steel vessel on a heating mantle, set up in exactly the arrangement that Les Case himself is doing in New Hampshire. On the monitor you see displayed, in fact, the mass spectrum from one of these samples. This is a relatively high level of helium-4. We compare the samples each day that we perform the analysis. We compare the sample of gas from the various active cells and blanks with a sample of room air, which we have measured many times and know to be 5.22 parts per million. If the helium is produced by a nuclear process, then necessarily there will be an associated release of heat. It appears that, yes indeed, in the vessel that was producing helium, there was some evidence of excess heat, and that the amount of heat produced was approximately quantitatively correlated, that is, the right amount of heat was produced compared to that of a nuclear process involving deuteron plus deuteron producing 1 helium-4 nucleus, which releases 23.8 million electron volts.
An experimentalist who has pioneered another promising cold fusion method, sonocavitation, is Dr. Roger Stringham of First Gate Energies. Using ultrasound frequencies, Stringham has observed extraordinarily high temperatures caused by the process of cavitation, where microscopic bubbles in water tunnel their way into target metals. Metals like silver, titanium, palladium, and platinum. are melted by intense heat created during the brief moment it takes for a bubble to collapse.
Well, this is a cavitation process going on in the bubble, and the acoustic energy is absorbed by the liquid, and there is a certain point in which it creates small voids which actually grow and then collapse very rapidly. And that is the cavitation idea. The temperatures that are required to create these ejectocytes are at least the melting point of the metal, and it looks like we are actually in the vapor phase, which is gaseous metal. And this amounts to, for the liquid metal, 1600 degrees Kelvin, and for titanium higher. For the vaporous state is several thousand degrees higher than that.
If these new sources of energy do turn out to be real, and I say there's possibly several different, totally different varieties, the question is, what effect will this have on our society, on the future? Well, it's just possible they may be no more than laboratory curiosities and can't be scaled up to commercial levels. I think that's rather unlikely. Nuclear energy was once a laboratory curiosity. So let's assume that these devices can be developed. The future is then almost unlimited. It could be the end of the fossil fuel age, the end of oil and coal, and the end, incidentally, of many of our worries about global pollution and global warming.
Right now, 2/3 of the cities has problem in pollution. And 1/3 of the land of my country is damaged by the acid rain. 80% of the power energy source is from coal. So this is a big problem. And right now we have 1.2 billion population, and we anticipate it will be 1/2 or more billion in the middle of next century. Right now, we consume 1 ton of the coal per capita. If we increase our power consumption by a factor of 3, we will burn about 5 billion tons of coal in the middle of next century. That's why I made my mind to do this cold fusion research. It's a big risk for me, but I think it's worthwhile to do it.
But what I like about cold fusion is it is different from thermal power, hydroelectric power, or nuclear fission power, because it is potentially small and the investments required are much smaller, and hopefully it can be mass produced by industry. And this completely changes the whole concept of power generation, distribution, consumption.
Examples of how these new energy technologies will replace fossil fuels are already in commercial development. In Vancouver, a small manufacturer of hydrogen cells called Ballard Power Systems has convinced major auto companies to switch to a system which is both non-polluting and eventually will be more economical. Although it is not a cold fusion device, the fuel cell is an interim technology that has been around for 150 years, but was only recently developed due to advancements in technology and the global environmental imperative. Cold fusion cells could easily take a similar pathway into the marketplace, with far more profound consequences, because it is millions of times more powerful than chemical energy per gram of fuel.
If we have a new energy source like this, which is capable of being made in very small units on up to large units, that's going to revolutionize our future energy supply. And energy is still basic demand. It's basic to our standard of living. And also, if it's a type of energy that doesn't pollute in terms of fossil fuel, CO2, greenhouse effect, all these things, as at least we currently envision the cold fusion energy source would do, it not only will give us this future energy source, but it's going to help us be good stewards of our universe.
It's history in the making, what we're living here. I mean, I couldn't dream of a situation like that. Can you imagine living at the time of Einstein and Curie and Bohr, all these great people were changing completely the science at the beginning of the century. And when I was going to school, to college, and all these things, it was like, it's over now, everything is done, just shut up and learn. And now, all of a sudden, I know that I don't have to shut up and I can do something in the field. I can bring my own contribution.
There's a curious parallel back at the beginning of the century. When the Wright brothers first flew in 1903, no papers covered it at all, because everybody was convinced, certainly the American press, that heavier-than-air flight was totally impossible. All the top scientists said this is nonsense. And editors wouldn't even bother to send journalists or photographers to interview the Wrights, or even to take pictures of them flying in full public view. And it wasn't for about 5 years that eventually they realized, my goodness, this is real. Heavier-than-air flight is possible. And I think a similar thing is going to happen with so-called cold fusion.
New Energy Institute, an independent, non-profit, public benefit corporation which provides information and educational services to help bring about a clean energy revolution.